Hello, these are the notes for Chapter 5, Section 1, Part A, and the Algebra 2 text. And we are going to introduce you to exponential growth and decay. Now, while you may have studied this in Algebra 1 at length, you've probably forgotten a decent amount. So I'm going to spend a little bit of time just kind of reviewing the basics. And a lot of this has been taken directly from your textbook. And hopefully it makes sense to you. Basically, you have either an exponential growth or you have a decay. I wish I made it like much bigger, but if you could highlight this is y equals a times b to the power of x. And what we're going to do up here is we are going to label these parts. Now, y, of course, is your output. And x is your input, and typically your input is time. It doesn't have to be time, but it's very typically, and sometimes I'll even use t for time in an exponential function. A, now your notes in your textbook do not really talk about this, but A is going to be your initial value. It's basically like how much money you start with. So let's say that you have a car that you purchase for $20,000. Once you drive it off that lot, it's going to decrease in value. But in your function, to figure out how much it costs after X amount of time, your initial value is going to be that $20,000. That is also going to be your y-intercept. Unless it has been shifted. So if it's been added, so like if you're adding 3 over here to the end, that's going to shift it up 3. But that is no translation, just in case we run into that later on. And then B is going to be either your growth or your decay. And we're going to talk about that in just a second. All right, so let's look at what a growth function is. Now, a growth function is going to be in this form. It's going to have the initial value. Sometimes it's 1. Sometimes it's something other than 1. It has to be positive, though. That's what this means. So your initial value does have to be positive. It can be a fraction or a decimal as long as it's positive. And then for it to be a growth, b has to be greater than 1. Now, I want you to just think about this. So let's say you have that $20,000 car. And this is not going to happen, but basically, when you multiply that by 2, it means it's going to double in value for X amount of time. So, it's probably something else. So think about something other than a car. Now, a car is typically going to do this. It's going to decay. So if I put 0.5 here, that would make more sense because it's going to lose value. It's going to lose 50% or half of its value. So for this to be a growth, b has to be greater than 1. Now let's take a look at kind of a generic graph of a growth. Now, if you look here, it says f of x is equal to b of, there's no a. There's not something that you can see. In this case, a is 1. So there's always a number in front of b. If you don't see it, it's 1. That is why your y-intercept is right there at 1. Now, growth, exponential growth, it's going to be slow at first, and then it's going to get big really fast. Exponential functions grow faster than any other function that we study in Algebra 2. Let's talk about the end behavior really quickly, though. So end behavior is the left extreme behavior, which would be over here, and the right extreme behavior over here. So let's look at the right side first. So as you notice, let's change colors here. If I travel to the right, I am going to the right, which is this notation. I am also traveling up at the same time. So if I'm traveling up, that means that my y value, or f of x, is going to approach positive infinity. So that's kind of like normal, and it's a growth, so it's going to grow, obviously, so it's going to get bigger and bigger. The left-hand side, on the other hand, is different than what we've ever had before. Notice that it is going to the left. So let me change it to green. So it's going to the left, but as it goes to the left, it actually doesn't go down like this one is. It actually looks like it's gonna even off at the x-axis. Well, what happens is that it gets closer and closer and closer to the x-axis, but it never quite reaches there. That's called an asymptote. And what happens is that it's getting closer and closer, but it's never going to touch it. It's never going to intersect it, which means touch. So it's never going to like go down here to this part of it. So it doesn't approach negative infinity. It actually gets closer and closer to 0. So as it travels to the left, your y values get closer to 0. So that's your end behavior here. Now, likewise, on the other end, if it's a decay, and I already kind of talked about the decay with the car. So let's say you've got a car, it starts out 20 grand, and it loses, I don't know, 80% of its value, which is probably not as much as it actually loses, but I digress. Anyway, so the initial value would be 20 grand. He's losing, now he's not losing 80%, he's losing 20%. So if it kept the same amount every year, you would just multiply by 1. Exponential equations cannot have a base of 1. And actually says this in the definition here. So it has to either be between 0 and 1, or it has to be greater than 1. So if it's greater than 1, it's obviously going to get bigger. But if it's between 0 and 1, it's going to decay. So imagine taking 80% of the value every single time. So the initial value would be 20 grand. The decay would be 20% loss, or it would be 0.8. So if you look at this one, it's very similar. It starts up here and it loses value, loses value, loses value. But if you notice on this side, it is getting closer to the x-axis again. You have another asymptote situation, but it's on the right-hand side because it keeps getting smaller and smaller. Now here's what's really gonna like mess with you. So let's say you have a caffeinated drink, and caffeine has a half-life. Just about anything that you ingest will have a half-life. What's going to happen, let's say you've got 400 milligrams, that's a lot, of caffeine, and it's going to half eventually. I don't remember how many hours it is, but it's like 4 or something like that. So it's going to keep halving. Half. Now, y'all know that if you have a calculator and you keep dividing it by 2, if you keep taking half of that number, is it ever going to reach 0? No, it's never going to get there. So that's what creates this asymptotic type feel to it. So as it travels to the right, it's going to get closer and closer to 0. But on the left, it's clearly going up. So as you travel to the left, you approach positive infinity. So that's what a decay looks like. And this is what a growth looks like. And all of this is theory, but y'all know in real life, not everything is perfectly going to be fit to an exact function. All right, so let's get into the mathematics of it all. So determine whether each function represents a growth or a decay. We're going to graph it in a second, but let's look at A. Now remember, your basic is supposed to look like this. This is kind of your generic form. I don't see 2 bases, I only see the 2. So what I can do is I can rewrite it so it'll make a little bit more sense to me. So if you don't see this number in front, you put a 1 here. Now that's going to be your initial value. And notice how I don't have any translation. I'm not adding anything to it. So that's also going to be my y-intercept. So I immediately know it's going to hit right here at 1. All right, this is my base. If the base is bigger than 1 and 2 is bigger than 1, that means we are going to grow. So this is a growth. And what I want to do if I'm going to graph it is I'm going to put 0 kind of right here. And I know if I plug in 0 here, and I'll show you. So if you plug in a 0 here, 2 to the 0 power is 1. So there you go. What you want to do is just pick like a couple of more points. You can use 1 and 2. Now listen, if you use like 8, 9, 10, if you use big numbers, 2 to the power 10 is much bigger than you think it is. So use kind of smaller numbers. I'm just going to do 1, 2, and 3. That's enough for me to find the curve. All right, I'm not going to work all of these out for you because you can just do this on your calculator in your head. So 1 would be 2 to the power 1, so y is equal to 2. And then 2 to the power 2 is 4. And 2 to the power 3 is 8. We should all have those memorized anyway. You can go backwards, okay? Nothing is off limit. Your domain goes all the way from negative infinity to positive infinity. The only thing is when you run into negative numbers, though, so you have 2 to the power of negative 1. Now, what your calculator is going to do is it's going to change this because you're not allowed to evaluate negative exponents. It's going to drop that 2 to your denominator, and then it's going to give you a value of 0.5 or 1/2. So I'm going to put 0.5 because it's easier to graph. Same thing if you type in the second one. So if you type in 2 to the power negative 2, it's going to drop it to the denominator, and it'll be 1/4 or 0.25. Now, when you graph this by hand, you should know that this is going to give you an asymptotic type situation. So it's going to, as long as it's not been translated up or down, it's going to hug that x-axis. So 0, 1, I've got that one graphed. Let's do negative 1.5. See how it halves right here? And then right here, and it's going to look like eventually it's going to touch it, but it will not. All right, it will not do it. You're just going to do your best because it's by hand. Okay, and then 1, 2, 2, 4. Here's where you're seeing this growth. So if you look at the y coordinates, it's going from 1 to 2 to 4 to 8. So 1, 2, 3, 4. So this would be 8. Now see, if I used 4, it'd be way off the graph. So you can always kind of tell what your growth factor is or your decay by looking at your y values on your graph. Hint, hint, that is in your homework, and that is how you graph it by hand. So let's look at this one. This is a decay. I know it's going to be decay. I'm also going to squeeze that positive 1 in here. There is no translations up or down, so I'm going to go ahead and just start with 0 and 1 here. But it's going to be a decay, so it's going to have this kind of shape to it. Okay, and then you can just simply use your calculator. When you put like 1/2 to the power negative 2, that's going to wind up being, I think it's going to be 2 to the power 2, which is 4. And I know that surprises you, but this whole thing, what you do is you write the reciprocal and it changes the sign. So it's just kind of like, you can do it on your calculator, but you should also be able to do it without a calculator as well. Okay, so reciprocal changes it to positive 1, so that's just 2. Now 1/2 is just 0.5. Decimals are just easier to graph. That's 0.25, that's 1/4. And 1/8. Do I know that one off the top of my head? I do not. Let me pause it. Actually, I do. I think it's 0.125. Let me know if I'm wrong. Okay, so let's go backwards. Negative 2, 4. Negative 1, 2. And you see, like, it's kind of opposite of what we had over here with our growth. But we're going to get small. Oh, just barely touch it. And you know it's going to get closer and closer, but it doesn't touch it. It's so hard to draw that free-handed, but on Desmos you can just consistently like zoom in the section, but it will never ever touch the x-axis. So it's kind of neat, but that's how you graph them by hand. Okay, so here's where I need you to practice a little bit. I do not want you to graph the function. Don't worry about that. I want you to be able to tell whether it's a growth or a decay very quickly. So pause the video and I want you to label 1 through 4 whether you think it's a growth or a decay. All right, so if we look at number 1, it's missing the little 1 in the front. So this 4 is way bigger than 1. So it's going to grow really fast. So this is a growth. This one's also missing the 1 in the front. Actually, all of them are missing 1, which is a little bit weird about this book, but whatever. Anyway, so this is 2/3. Kind of hard to see it. Got it cut off, sorry. It's between 0 and 1. So if you multiply something by 2/3, it's going to get smaller and smaller and smaller. So that is a decay. If you multiply something by 0.25, obviously it's going to get smaller. So this is a decay. It's between 0 and 1. And then 1.5, if you multiply something greater than 1, it's going to grow. It's going to get bigger. So this is a growth. So now you know how to identify just by looking at function whether or not it's a growth or a decay. Let's get into the models, all right? Here's the good news. The models are actually on your formula sheet. You do not have to memorize these formulas. So there's only one difference. You've got y equals a. Let me write underneath it. So it's y equals a. This is normally written as b. So b is complex because either you're adding something to 1 to make it grow, or you are subtracting from 1 to make it decay. So what you can do when you're asked to write a model or interpret a model, so in this lesson we're interpreting a model. So for instance, that's your model. You need to figure out first of all if it's a growth or a decay, and then you have to tell me exactly what percent increase or decrease it has. And this is a little bit more complex, and I'm going to tell you right now, the exponential growth is much easier. Everybody, it's just so like natural to you, but the decay is what gives people trouble. So just kind of watch out for any kind of a decay problem. Speaking of decay, this first one is a decay. So let's look at this problem. So we're talking about a car. So the value of car Y in thousands of dollars, because I looked at that and I was like, there's no way this car is 25. It's actually $25,000. Can be approximated by this model. So I'm immediately going to write this down. It's too small for me. And see how they put a little t here. Now, if you're typing that into Desmos, just use X instead of t, and you'll be fine. So it says t is time and time in years, and that's important when you're interpreting the problem. So it says determine whether the model represents a growth or a decay. Well, it's a car. It's going to lose money. It's going to depreciate. You can tell by immediately looking at this number here. It's less than 1. It's specifically between 0 and 1. It is not losing 85%. That's what's kind of confusing about a decay. So if you look at your decay model, I'm going to write underneath it y equals a. So a, your initial amount was the $25,000, but instead of writing 0.85, I'm going to put 1 minus r. Okay, so what that means is that 1 minus r, your decay, is equal to 0.85. That is the result of whatever you're losing. So this is technically what you're doing. Now you can actually reason this out in your head, no problems. Now if you use your calculator, you wind up with negative 0.15, and you have to change this to a positive r, so divide both sides by -1. And you get 0.15. This is the percent. So 0.15 is 15%. That is what you are losing. That is your percent that you're losing for each year that the car was purchased. So every year that passes after that $25,000 original purchase, you're losing 15% on that car. So it says identify the annual percent increase or decrease. So this is going to be a decrease, and is a decrease of 15%. If you put a decrease of 85%, it is incorrect. So just be really careful. Now, if you don't want to use the 1 minus r thing, you have to reason it out in your head. You have to think, what minus 1 gives you 0.85? So if you start with 100% of the value and you subtract, or if you take away 85%, that means you're losing 15%. This 85 is what you're keeping, okay? That's what you're maintaining. So you're keeping 85%, but you're losing 15%. So that's kind of how you reason it out in your head. Then it says estimate the value of the car when it will be $8,000. So what you need to do, once again, is really understand what this model is asking you to do and how to use it. It says estimate the value of the car. Now, the value of the car is y, not t. T is time. So we're looking for t. So t is going to stay a variable, but I know that y is 8,000. So what I'm going to do is I'm going to go straight to Desmos. I'm going to go straight to Desmos, and I'm going to graph this right here, and I'm going to graph this one. Now, I'm going to warn you, if you put a T, I don't think it's going to work. So I'm going to replace T with an X. Go ahead and go to Desmos, graph both of these, and we're going to talk about how to find the answer. Well, I'm just going to be honest with you. Desmos got me. It actually worked. So it's a lot more flexible than a regular graphing calculator would be. So if you put an X here, see how it gives you the same thing for T. So that's really awesome. Note, take a little note right here. See this y-intercept here? That is your initial value, which is $25,000. And it's going to drastically decrease in price, and it continues to fall. Notice how your y value keeps getting smaller and smaller and smaller. And now in real life, it's going to be like nothing. It's going to be worth nothing eventually, like after 50 years. So let's go ahead and answer the question. So it says y should be equal to 8,000. So right now at this moment, here's where I'm going to figure out if you're paying attention or not. So if we say that y is equal to 8,000, we're saying the car is going to be 8,000. But the way our function is set up is that this is in thousands of years. So if it's 25 here, not 25,000. So how do you write 8,000 in thousands? So technically, you gotta get rid of that. So it's technically 8 represents 8,000. So let me go back to my home view here. Almost fell for this trap. So there's no way it's going to start out as 25 and then go to 8,000 if it's a decay. So that kind of helps a little bit. So 8,000 here is this blue line, and you see where it connects. That's going to give us our solution. And it looks like when it's worth the y value, that's 8,000, it's going to be a little after that 7th year. So 7.011. Okay, so I'm going to go back over here, and I'm going to write down that it's going to be approximately, let's use the right notation. So about 7 years, a little after 7 years would be when it would hit that $8,000 mark. Now let's fix this. Now if we type this into Desmos, this is going to give us the wrong result. So what we need to do is we need to correct it, and we need to say it is actually y is equal to 8, which means 8,000. So just be careful about that. And this is kind of like a big ideas textbook thing. They do like to trick you, so make sure you're paying attention to the small details. All right, so to the last example of the day, we're talking about population in millions. Now, typically population is a growth. It doesn't have to be, but in this case, it definitely is a growth. I can look at it and I can tell right here. We also need to pay attention that this is not actually 28.22. It's 28.22 million. So I'm going to put a little side note here, which means when I find out 30 million, I'm going to use P equals 30 when I type that into Desmos. I don't know if Desmos is going to use P or not, but I'm going to try it and we're going to find out. Okay, so we've already established this is a growth because this is going to be greater than 1. So I know that this is a growth. So the math part of it is that we are going to figure out exactly how much this is growing, and a lot of you can just do growth in your head. So the model for growth is y equals a. Your initial amount's 28.22 million, but your growth is 1 plus r. So all you have to do is simply think 1 plus what number equals 1.01. Now mathematically you're just subtracting 1 and it's 0.01. So your growth is going to be 1%. 1% growth. So teeny tiny growth. All right, let's go to Desmos. I'm going to go ahead and see if this will work. If not, I'll just change it to f of t or y, because I know that will work. And I'm going to type in P equals 30, not 30 million, because it's not going to fix my model. Okay, well, Desmos is really cool. So I typed it in exactly as it said. Unfortunately, though, like on the home screen, I can't see it. Now, y'all need to realize that you might want to zoom out a little bit because it does hit at up here at 28 on your y-axis. So let's go ahead and type in P equals 30, which represents 30 million. Oh, see, now it's not working this time. I think I'm gonna have to do y equals. Let's see what happens. There it is. All right, well, there's the limitation. All right, we're gonna click on this, see where it intercepts. That's going to give us right there. So we want exactly 30. So 30 million means that it's going to take about 6.147 is it years? Let's see. Yep, number of years since the beginning of the decade. So we're going to write that down one more time. I already forgot what it was. So 6.147. All right, we just had to change that into y equals 30. So the time is approximately I already forgot it again. No, 147. So a little after 6 years, and that is it. So you just got a handful of questions. Now I just want to tell you on your practice, please do not graph these. You can do these like in like a minute or two. So this assignment's not going to take you very long. And if you got any questions on 17 or 18, just please let me know. Y'all have a good day.